Hello, welcome to another module of this course, Microwave Integrated Circuits. We are now in the week 6. This is module 4, week 6. In the previous module, we had discussed about stability and what are the conditions for unconditional stability and what is the condition for just keeping the circuit stable. So let us review once again what we mean by stability. We saw that if gamma in modulus is lesser than 1 or gamma out modulus is lesser than 1 for all mod gamma s lesser than 1 and mod gamma l lesser than 1. So this is the stability criteria, that gamma in should and gamma out modulus should be lesser than 1 for all gamma s and gamma l modulus lesser than 1. If modulus of gamma in or gamma out is more than 1, then it is not stable. So this is the condition for unconditional stability. Fine. So then can we say that the condition that gamma in, which is a function of gamma l, modulus becomes equal to 1, this is the boundary between unconditional stability and potential instability. Gamma in as a function of gamma l modulus equal to 1 is the boundary between unconditional stability and potential instability. What does that mean actually? It means that when gamma in as a function of gamma l, so those values of gamma l for which gamma in modulus becomes equal to 1 is that boundary. So if we can find out the locus of those points or locus of gamma l for which modulus gamma in is equal to 1, then we find out which is that boundary. So if we want to derive the equation for that locus, let us see what it is. So the condition that we have to satisfy is, now gamma in, as we have seen earlier, can be written as after a lot of mathematical manipulations, what we can write is first thing that you have to note is this term is a constant, and let us say call that CL. This is a vector quantity, and this term is also a constant. Let us call it RL. This whole term can be written like this whole equation is simplified like this. This is the equation of a circle. So in other words, that boundary that I was mentioning between stability and instability, between unconditional stability and potentially unstable circuit, is a circle. The equation of this equation of circle that I just mentioned is also known as the output stability circle. It is called the output stability circle because here the circle is dependent on gamma L, which is the output impedance connected to the output of the amplifier. Now similarly, we can also have the input stability circle, which is analogous to the output stability circle, but instead of gamma in becoming equal to 0, we will have gamma out modulus equal to 1. So, let us see, suppose this is our Smith chart, okay. This is the unit circle in the Smith chart, and this horizontally shaded region is our output stability circle. Now, I said that the boundary of this circle, this output stability circle, determines which is the unconditionally stable and which is the potentially unstable regions or potentially unstable values of gamma L. So, either gamma L values inside this circle will be unconditionally stable, will lead to unconditional stability, or they will lead to potentially unstable situations. Now, which one of these? Is it the outside of this circle or is it the inside of this circle? Which is the stable and which is the unstable region? So, to do that, we need to find out, if we see this figure, note that when gamma L is equal to 0, gamma in becomes equal to S11. So, in other words, S11 represents the value of gamma in when gamma L is equal to 0. So now note that either outside this circle, either modulus of gamma in will be lesser or greater than 1. And since S11 represents the value of gamma in for gamma L equal to 0, therefore, modulus of S11, recall that S11 is the value of gamma in at the origin. If the modulus of S11 is lesser than 1, then the point gamma L equal to 0 is stable. On the other hand, if the modulus of S11 is greater than 1, then the point gamma L equal to 0 is potentially unstable. So, this is the case. If modulus of S11 is greater than 1, then it means the inside of this circle, the stability circle, this output stability circle is stable, whereas if modulus of S11 is lesser than 1, then it means the outside of this output stability circle is the stable region. Now, here this blue region shows those values of gamma L outside the output stability circle, but inside the Smith chart having unit radius. So, once again, if modulus of S11 is greater than 1, then the outside of this circle is the potentially unstable region, because the origin, the value of gamma in at the origin, that is S11 modulus itself is greater than 0. Hence, the origin point must lie in the potentially unstable region. If the origin in this case lies outside the stability circle, then that means every point outside the stability circle is potentially unstable. And just the reverse in this case, where if modulus of S11 is lesser than 1, then it means the origin point lies in the stable region, and since the origin point lies in the stable region and the origin itself is outside the output stability circle, hence all points inside the output stability circle must correspond to potentially unstable state. Now, similar to the output stability circle, as I was mentioning, the input stability circle the equation of the input stability circle is given as recall that gamma out is given like this. And on simplification, this equation reduces to which in turn can be written as so again this point corresponds to Cs, this is a vector quantity, but this whole thing is a scalar corresponds to Is. And recall this is called the input stability circle because the locus of this circle is dependent on gamma S, which is the input of the which is the impedance connected to the input of the amplifier. Let us see another case of the stable and of the stability circle and the Smith chart. In this case, this is the input stability circle because and we are in the gamma S plane. The input stability circle does not touch the Smith chart with unit radius at all in this case. So, the locus of this input stability circle corresponds to modulus of gamma out equal to 1. Now, again we have the same problem, which is the potentially unstable region and which is the unconditionally stable region. Now, note in this case that since it does not touch at all, there are no intersection points between these two circles. Hence, all possible design values, all possible values of gamma S will be either all stable or all potentially unstable. Unlike in the previous case where there was a intersection region between the two circles, so there could be some points within this unit circle of the Smith chart which could be stable unconditionally or which could be potentially unstable, I beg your pardon. So, again the procedure to find out the stable or the unstable regions is the same as the case when we dealt with the output stability circle. If modulus of S22 is lesser than 1, then that means the gamma S equal to 0 point is stable, because at gamma S equal to 0 we have gamma out equal to S22. Hence, if modulus of S21 is less than 1 and if our input stability circle and Smith chart have positions like this, then that means that all points within the Smith chart are stable. If modulus of S22 is greater than 1, then it means all points inside the Smith chart are potentially unstable. Now, you might ask me here, we were talking about the stability circle being the boundary between stability and instability, then why are we discussing about this Smith chart with its unit circle? The reason we are discussing it is because every value, recall, in addition to gamma in and gamma out modulus being lesser than 1, we also have to satisfy the condition that modulus of gamma S and gamma L should be lesser than 1. In other words, gamma S and gamma L should lie completely within the Smith chart of unit radius. So, that is also the condition that must be satisfied. Now, stability, this is an interesting diagram showing the variation of stability with frequency. Now, this is the circle, okay, this small circle with small radius is the input stability circle for frequency of 14 gigahertz. this circle is the input stability circle for f equal to 7 gigahertz, and this circle is the input stability circle for f equal to 1 gigahertz. Now let us see at 14 gigahertz, we see that the modulus of S22 is lesser than 1. Hence, for 14 gigahertz, all regions outside this input stability circles, that is, all these regions must be stable. For f equal to 7 gigahertz also, we see that S22 modulus is lesser than 1. Hence, all regions outside this input stability circle must be stable. However, for f equal to 1 gigahertz, S22 modulus is greater than 1. In other words, what it means is that all points outside this stability circle are potentially unstable. Hence, it is not that just by seeing whether a point is outside this circle or inside this circle, we can determine whether it will be stable or potentially unstable. If we just rely on the curvature, then we may not always reach the correct result, as in this case. In this case, for the f equal to 1 gigahertz circle, points inside the circle are stable, whereas for f equal to 7 and for f equal to 14 gigahertz, points outside the circle are stable. So, in this case, this is another interesting case of the position of the Smith chart and the stability circle. Here is our input stability circle and here is our Smith chart. Now, one possible way how this input stability circle can be sit is if it is concurrent with the Smith chart. In this case, we can write the condition of stability, condition for unconditional stability, provided modulus of S11 or modulus of S22 is lesser than 1, is that the difference between the distance of the center from the origin and the radius of the stability circle, if that is greater than 1, then the points inside the Smith chart are unconditionally stable. Let us see the case here. In this case, the center is at this position. This circle does not touch the Smith chart. So, the radius, if I subtract the radius from the distance of the center of this circle from the origin, and that will be greater than the radius of the Smith chart. Hence, this condition is satisfied. Similarly, in this case, the circle, the stability circle is concurrent. Its center is at the origin. However, its radius is greater than that of the Smith chart. Therefore, it is also all points inside the Smith chart are unconditionally stable. In fact, that new criteria that I had mentioned earlier while discussing unconditional stability is that it measures, recall that mu given by this equation has to be greater than 1 for unconditional stability. Now, these two cases that I just mentioned are the case for unconditional stability, that is, all points inside the Smith chart will always be stable irrespective of what load I connect. So, this parameter mu defined like this actually measures this difference between the position of the center from the origin and the radius of the stability circle. If mu is greater than 1, then it corresponds to either that this stability circle has its center at the origin of the gamma s or gamma L plane, and it has a radius greater than the radius of the Smith chart, or that this stability circle is completely outside this Smith chart, and therefore it also satisfies the condition of modulus of the position of the center minus the radius of the stability circle being greater than 1. Now, if you have your stability circles like this, suppose your output stability circle is touching a constant conductance circle, say I call that some value of conductance corresponding, say the conductance is 1 upon Rb, and the input stability circle is touching a constant resistance circle corresponding to resistance Ra, then it is potential, this is a potentially unstable situation. There are some values within the Smith chart for which the circuit is stable, both for some values of gamma s and some values of gamma L. But if we connect a resistance Ra in series so that it adds more resistance to the input, or if we add a conductance corresponding to 1 upon Rb in shunt at the output, if we do that, then our stability position of the stability circles, it can be shown that the position of our stability circle shifts like this. In some cases it may not be possible to obtain. For example, if our input stability circle is like this, it does not really touch any constant resistance circle. Or if say our output stability circle is like this, here also it does not touch any constant conductance circle. However, they do touch, say this circle, even this output stability circle, even though it does not touch any constant conductance circle, it does touch a constant resistance circle, and this input stability circle, even though it does not touch any constant resistance circle, it does touch a constant conductance circle. And if we show it like this, so this is the, so 1 upon Ra is the conductance circle which this input stability circle is touching, and Rb is the constant resistance circle that this output stability circle is touching. Then if we connect Rb in series at the output or 1 upon Ra in shunt at the input, any one of these have to be done, not both. Even in this case, when we were connecting series resistance at the input and shunt resistance at the output, any one of the two has to be done. So coming back here, when we have a case like this, where input and output stability circles do not touch a constant resistance or constant conductance circles respectively, however they do touch a constant conductance and constant resistance circles respectively, then if we connect a resistance Rb in series at the output or a conductance 1 upon Ra in shunt at the input, then again we can shift the positions of this stability circles so that they become like this. So in summary, we see that stability is a very important aspect of an amplifier design. Unless an amplifier is stable, even if we achieve a certain gain, then that gain will not be sustainable. But the important thing to note here is that when we discuss about the stability circles, we divide the Smith chart into various regions, potentially unstable or stable regions, and we do not get any unique solutions for the stable or unstable regions. In fact, we get a boundary between the stable and unstable regions. So we have lots of values of gamma s or gamma L to do our design with. Since we have so much allowance in choosing gamma s and gamma L, we can choose the value of gamma s or gamma L that we finally choose. We can include other parameters like gain or noise, as we shall see later on. So stability design from a stability point of view, just to emphasize, it does not give a unique value of gamma s or gamma L. It just gives a region, and we can choose from these regions those values of gamma s and gamma L that give us the correct gain or noise figure. Thank you.